record. And that is Daniel. And I'll just watch that for a minute. Okay, so we did have homework due today. There will be no lab on Friday. If you have any questions about doing the cross sections, first place to look would be, there's a whole bunch of stuff in the Lab 4 folder called cross sections. I would look at those PDFs first. The layers, I've got a decoder for the layers. If somebody reminds me, I'll send it out to the class telling you which color layer is what. OD is contacts. Yeah, I should do that. Just send that out to everybody. The week 2 of the lab, which will be the week after this one, is where we look at layouts and we have to figure out what the schematic is. So doing that and then put those 4 schematics into Pixis. Doing that, you have to be able to identify a transistor, where the drain of the transistor is, where the gate is, what is it connected to, and drawing the schematics. I'm sure in those files, those 8 or 9 files somewhere, there is one of them, those PDFs is related to how you read the schematics. So you may have to do some digging. I've narrowed down the information for you quite a bit. But if you have any specific questions, I will be available. I'm pretty much done loading in my classes for the semester. I always get done early, so I can spend the last few weeks watching you guys panic is my official job title, and helping you out. Don't worry, that having everything loaded in the BB Learn kind of takes my stress level down a good bit. And and being able to do research in the fall takes my stress level down a little bit. And being able to work on research in the summer takes my stress level down a little bit. So, but yeah. Yeah. I like to plan ahead. I'm one of those people who really likes to know what's going on in advance so I can plan things out. I'm mentally, you've been in my office, you know what a mess I am externally, but inside my head, I know what's going to happen and what's going to happen next. And I'm already planning for the next step. And I'm keeping up with that. If someone throws me like, this is the classes you're going to be teaching a week before classes start, I go into panic mode because I haven't planned out what in my head, what I need to get loaded, how I'm going to organize the class for that semester. You know, all that stuff happens before I write it down on paper. Then I just go write it down on paper and it's done. I like having things, I like knowing what's going to happen. Things have been bothering me a little bit lately, so I will let's just leave it at that. Homework 8 is due a week from today. That will be exam review day. Homework 8 requires more writing than problem solving. So it's basically reading some things and answering, probably watching a video or two and writing down what you learned about it. So no real high stress homework there. In fact, you could probably do that now if you wanted to get ahead a little bit. Exam 2 is on Thursday, March 25th. I've gotten an email from one person saying they wanted to do it remotely and no one else has contacted me yet. So please just send me an email so we can make an appointment that fits both of our schedules. The Tuesday after the exam, Dr. Cambo's coming in and he's talking about the technology it took, the processing technology it took. He's better with the processing end, I'm better with the circuit end. The processing technology it takes to get down to 3 nanometers and what Samsung is doing to go down to the next node beyond that. And it's mostly Samsung and TSMC that are able to make transistors at that fine of a level. So it's a really interesting talk. So he will be in here. Last fall, he actually came in person. And I thought that would, yeah, so You get more contact with the students in person. And then what else? And if you're interested in what he's doing, he's mostly doing cybersecurity, but he's doing cybersecurity from the viewpoint of using the hardware and the software together. And so there's a lot of physics, there's a lot of hardware engineering, electrical engineering, there's a lot of software engineering involved, and we all kind of work together in the lab, which is more like the way people work in the real world. And then we go through, and then this is almost the end of the semester on the schedule. If you're interested in the Accelerated Master's Program, contact me or talk to your advisor. I can send you the name of the graduate advisor's email. I can't spell it. His name's Slava, but that's just a nickname. Exam 2, already posted on BB Learner, the exam review and the solutions to that, lecture slides and solutions, and all the homework and solutions. At midnight tonight, you'll have all the mathy problems, the circuits problems you need for the exam 2 already. And you get 2 sheets of notes. I would highly recommend including the sheet from the first exam and then starting a new sheet for this exam. This is Cedra Smith. I've had this conversation with Dr. Campos several times. Cedra Smith still uses planar transistors. And I was fighting that for a really long time. I wanted to upgrade this class and use FinFETs, because FinFETs is what everybody's been using for the past 5 years. But it's true with the planar transistors, the devices we've been studying, the equations are still the same. The models inside of SPICE are still the same. The small signal model still looks the same. They're still valid for the way people build transistors now. Now, and this slide is out of date since like last year. I can tell you what's going on. The first step of this was what we do is we take that planar transistor, and I hope I can draw. Yay. We take that planar transistor and instead we turn the gate on its side like this. And we put an insulating layer down here. So now this is insulator. And this is the gate, in case you didn't catch that verbally. And now I've got a capacitor, we're wrapping our poly around that. We've got an effective gate width that's 3 dimensions of the transistor. And putting that insulating layer there meant that we couldn't get electrons from the bulk coming up and interfering with our transistor action. So both of these things together made transistors so much more ideal that even though it's more expensive to do the processing, people bought this because it makes better circuits. Their output resistance gets better. All kinds of things improve greatly. So the logical conclusion to this last year was that Samsung said, okay, we're going to take this raised gate, and instead of having it on 3 dimensions, we're going to have gate all around. So I have 4 sides of the rectangle are the gate of that transistor, and you're controlling, this is the drain over here and this is the source. And this was what they were going to do, was going to build nanowires. And then they found out these things don't work so well when they actually put this into practice. So their fix for this, and this was like as of 6 months ago, was to turn these nanowires into very thin nano sheets. They made them a little bit wider and everything corrected itself. So that's where Samsung is at as of 6 months ago. We'll find out where they're at as of a week ago when Dr. Cambo comes and talks to us. Because he keeps up, this is part of his daily routine, is just keeping up with this stuff. This is an op-ed. I could make your entire exam 2, just give you this and ask you various questions about it, but I haven't done it so far. I put this on the 490 exam. It was a bonus question. 1 point extra credit, calculate all the voltages and currents in this circuit.
That was from last fall, wasn't it?
What?
That was from last fall, wasn't it?
I probably did that last fall too.
I remember.
Okay. I did that the last exam in there too. Okay, now this is a 3-stage op amp. When we want to start trying to decipher circuits that look like this, we start by looking for the gain stages. And the way we can do that, I mean, looking at something like this, I look for something that's labeled VN. And there's a VN minus, and there's a V out. And that tells me it's probably an amplifier right there. And then I start looking for circuit structures that I can recognize, like a diff amp stage right there. V out, I see an amplifier stage right there. A lot of this up here, this is a current mirror. And a lot of this down here is a current mirror. And you start picking these things off, and you can just do it one by one. And labeling them, you can start to figure out what a complex circuit is doing. So let's do this with something a little bit more reasonable. This one here, I've got the resistors in there, and I've got ideal current sources. Now I want to figure out where the signal path is. So I start with, I've got V1 and V2. I know that's a differential amplifier, that some of the signal's coming off of here, but the output's going to come off of the drain of that one. And I follow the little line of the signal path through here. And then I can look at this and I can say, okay, stage 1 is a differential amplifier. I just have to recognize that one. Stage 2, if I look at this, the input signal is going in on the gate and it's going out on the drain. So this is a common source. This is a high gain stage. We figured that part out already, high gain. And then I look at stage 3, and my input's coming in on the gate and the output's coming in off of the source. This is a common drain. This is a buffer. It's acting, the common source has a high RO, which we don't want our user to see. So we put the buffer in there to give us a low RO, which is more desirable. I need the high RO to get the gain, but I don't want the end user to have to deal with a high output resistance circuit, so I buffer it. Okay. This is a schematic that has actually shown up on exam 2 before. And this one is more along the lines, instead of calculating current and voltages or stuff like that, can you describe what this is doing? Can you tell me what each one of these transistors are doing in the circuit? Again, my first step is to follow the signal path. So my input, this is my input here, plus and minus. This is a diff amp. So Q1 and Q2 are diff amp. They're gain stages. Following that signal path, I'm going into the gate, and my output is right here because it's labeled V out. I'm coming off the drain, so this is a common source. Okay. Everything else in this circuit is a current source. Everything that's not a gain stage is a current source. We can see a current mirror up here. This is providing current. This is my current source for the diff amp. And down here, current source. I didn't want to put CS because that means something else. And down here, I have an active load, which is basically a current source too. The capacitor's in there on purpose. It is called, and this is something we'll talk about after exam 2. It is a compensation cap. What this does is this whole circuit right here has a huge mess of poles and zeros in it. that generates a Bodie plot that I'd be proud of if you could do in 280. It's the 280 like Bodie plots, right? I don't want to have to deal with that in the real world. So what I do is I put this compensation cap in there. It puts a pole at a frequency that is much lower than all the other poles and zeros. So what happens here is when I draw the Bodie plot for this whole circuit, it looks like this. This one's just determined by CC. All the rest of the mess of things going back and forth like this in the Bodie plot is at frequencies I don't care about. So I'm just making the Bodie plot look better. And I'm also controlling the stability of the circuit. I lose some bandwidth, but I'm going to gain some stability.
Is the Bodie plot for the common source?
This is the Bodie plot for the whole amplifier.
Oh.
Yeah. There's a big mess at the end. That's what that represents, is the big mess at the end. I put this frequency, the compensation cap puts a pole frequency at a low enough frequency that I can ignore the whole big mess of what's going on the inside.
Oh, okay.
The 741 op amp, on some of the older op amps, they used to have 2 pins on the little 8-pin package that were designated so you could put your own compensation cap in. And if your op amp started oscillating, that was your first line of defense, is just stick a cap there. That always works. It's like magic. And then you kill your bandwidth, and then you have to think about what you're doing. Okay, differential and multi-stage amplifiers. I digress to the real world again. That MOS differential pair, it's a really important circuit. It is the heart of the op amp, and the op amp is like the most basic building block of analog electronics. So we're going to start looking at the small signal operation of the MOS differential pair today, and we'll throw in the active load, we'll throw in the current mirror load, and then we'll look at multi-stage amplifiers, and then we'll break for an exam. So this is the basic progression of how this worked. We started out with the idea of a differential amplifier on a circuit board using discrete resistors. So this is a differential pair with a resistor load. When I build this inside an integrated circuit, there's two ways I can build it. I can build it with, this is called a current source load. And this one over here, C, is called the active load. The only difference between the two, I put the strap on here between the gate and the drain, which means my drain voltage here is by default VGS. I have a single-ended output off of this one, whereas on the other one, the current source load, I have a differential output. Now, since the big idea for analog electronics for the past, since 1962, has been op amps, and still is, only just the op amps are getting better, is I have a differential input and I have a single-ended output. This is what gets built as the heart of an op amp. Next thing I'm going to do is I'm going to put a high gain CS stage on it, then maybe a buffering common drain stage on the output, and put some stuff in there to stabilize it for temperature, maybe make the input impedance super high, put a JFET input on it, build little tricks into these things to make them better for different applications. But that's basically how every op amp starts out with, is that circuit right there. This is next to impossible to build because I can never match the resistors. Back when I was in college, that was like one of the jobs for the grad students, would be to sit there measuring resistors, the 0.1% resistors, to get the precision matching and find the two that match the best so they could actually build an amplifier. Yeah, we don't have to do that anymore because we have the magic of transistors. Just like we don't do TTL anymore. The whole idea behind this op amp, I have two different kinds of signals coming in here. I have the difference between the two inputs, and I'm going to draw it like a real op amp. That's what I want to amplify. I want to amplify VID. And then whatever noise is actually, I'm going to call it noise, even though that's a bad word. And then I'll explain why noise is a bad word in 490 in the fall, if I get to teach it. Any common signal I've got between the two is just going to be noise. It's noise that gets on my positive input, and noise that gets, and that's not really drawn electrically correctly, and noise that gets on my negative. This is V common mode. This is what I want to attenuate. And Cedric Smith is confusing, and Dr. Brower wrote that. Yeah, this will give you an idea of what kind of guide you're reading through Cedric Smith, is to help you out. But I can't go through, I'm going through like 4 chapters of Cedric Smith this entire semester. And I'm going through it at a depth that you guys can maybe like concentrate on. If I went through Cedric Smith in detail, going through every equation and every derivation, I'd maybe get through 1 chapter a semester, but you need more than that. So I'm kind of trying to do this at a higher level. The large signal operation, there's going to be limits on how much differential signal I can put in here. I mean, eventually what's going to happen is I'm going to rail, I'm going to saturate, I'm going to go to my high power supply or my low power supply. So there's limits to how much voltage I can put on here before I hit those rails on the output. And we also need to keep all the transistors in saturation to avoid saturation from happening. I'm sorry. This is a MOS differential pair. We want to start out drawing the DC bias circuit. So for DC, I ground all the AC sources, or I short them out at their voltage sources. So my AC voltage source, my signal source, is going to be this VID. I'm just going to short this out, and I'm going to short this one out, and I'm going to have V common mode both at V gate 1 and V gate 2. The DC source will still be working, and so that is the DC circuit right there. Yes. Okay, that's the DC version. Now I'm going to erase that. Is everybody okay? Because this will be like on the slides. I'll be on the I am recording. I'm going to erase everything. And now we're going to draw the AC version of this. So here is the AC version. For the AC version, I short out my DC sources, which is my common mode source. So this is just basically going to ground. My DC power supply up here is also going to ground. It is an AC ground. DC sources are AC grounds. DC voltage sources are AC grounds. What happens down here? This DC current source becomes an open. So there is my circuit right there. Do I have a better picture of this on the next slide? I certainly hope so. Yeah, well, that's the DC bias circuit. That's the DC bias circuit redrawn neatly. Now, in this case, I'm given V common mode is 0 volts. Let's annotate the schematic first. That will help us figure out what's going on. My VDD is 1.8 volts. Doing this on the exam will save you a lot of headaches and a lot of time. VSS is negative 1.8, because you'll see things that suddenly you know. I is 100 microamps. We have the same voltage at the gates of each one of these transistors. Everything's matched. So that 100 microamps is going to split perfectly in two and give me 50 micro over here and 50 micro over here. Okay, sorry, my internet connection got lost and Zoom went away. I'm probably not sharing the screen. Share screen. Okay, we're there and we are recording. Okay. Okay, we did get that part back. So we got this far. It's better than my computer crashing. RD we're given is 6K. It's 6K over here too. VGS is 0.6. So that is telling me this, the difference between these two voltages here is 0.6 volts. We're getting a lot of information given right here. 0.6 volts. And the threshold voltage is 0.4 of a volt. Now I'm also given V common mode is 0. My internet connection is unstable. Gee, I didn't know that. Okay, my V common, sorry, I gotta laugh at technology. I'm the slave to it right now. My V common mode is 0 volts, which means this is also 0 volts. So there's a lot of things I can deduce. And I'm changing colors. Let's go to black. Okay. One thing, I've got 0 volts here. I drop 0.6 of a volt. This must be at negative 0.6 volts. I've got the voltage on one side of a resistor, the current drain and the resistance. I can calculate VD. It's 1.8 minus 6K times 50 microamps minus the IR drop across there. What does that come out to be? Did I do that? 1.5 volts. And they're identical on both sides, so this one's also 1.5 volts. Okay. What else do we know? If I raise V common mode, if I make it 0.2 volts instead, let's go to red. I don't have a red. Oh yeah, I do. There it is. If I make it 0.2 volts instead, it doesn't change anything here. It 1.8, the 6K, the 50 microamps doesn't change. The 1.5 volts doesn't change. The only thing it changes is this voltage right here, 0.2. This would become 0.2 volts. Now I have 0.2 minus 0.6. This is going to go to negative 0.4 volts. The only thing V common mode is going to change is the VS of those two transistors. Okay, why was that important? I don't know. We'll get to that.
So the current across both those is to just be split across the two branches evenly, right?
Yes.
Okay.
As the current will split across the two branches evenly as long as the voltage on the two gates of the transistors is the same.
Mhm. If
I put a differential signal across there, that's no longer true. We will get to that today. I took an entire senior level course on this one circuit. It's hard to do this all in one day or in a couple of days as we've done. What do we know here? We want to keep the transistors in saturation. Okay, so in order to, this voltage right here, we've already calculated has to remain at 1.5 volts because as long as there's 50 microamps through here and 50 microamps through there, and the same voltage at the power supply, then VD has to obey Ohm's law. It's got to be 1.5 volts. So we've got VD. Remember to keep the transistor M1 in saturation. And
one of those
It's one of those days. To keep M1 in saturate, let me just come back to this. We know everything's the same. Slide 14, I will reboot and see you un momento.